very mad at me. All right. So waves, like light waves, light moves at a constant frequency. That frequency, not the frequency, the speed of light is about 300,000 kilometers per second. So the world is not 300,000 kilometers long, so it takes less than a second for light to travel across the world. But if you've noticed, there's a delay on things like Zoom. Well, that delay isn't because it takes long for the signal to travel. What's taking a while is for the signal to get processed by the computers that have to process the signal. On Zoom, on TV, you see everyone is talking remotely to each other on TV, and there's always this delay. And that delay is because of the processing, not because of the speed of light. So these are all different wavelengths, right? Red, orange, green, blue, violet. You notice that red has a really long wavelength, okay? And so therefore it has a low, what's called a frequency. And purple has a really short wavelength and it really has a really high frequency. All right, there's infrared light that would be beyond red, that would have a longer wavelength and even a lower frequency than red. We can't see it, but we can feel it as heat. All right, what we feel as heat is infrared energy. And then there's ultraviolet, that would be beyond violet. That's a higher frequency than violet and a shorter wavelength, and that will end up having an impact on things like our cells and the DNA in our cells, and that causes us to get cancer, skin cancer, things like that. So wavelength, and I asked about it in the bell work. I mentioned it just now, talking about the different wavelengths of light. So the wavelength is a measurement from wave to wave, from the same part of the first wave to the same part of the second wave. So this is called the crest of the wave. You can measure from crest to crest. You can measure from trough to trough. You can measure from the middle of one wave as it's descending to the middle of the next wave as it's descending. That's a pain to measure. It's easiest to measure from crest to crest. From the top of one wave to the next would be the wavelength. So here we can measure the wavelength, crest to crest. That's the wavelength. You notice that in this first wave, the wavelength is longer than in this one. If everything else is equal, a longer wavelength means lower frequency. Meaning if you are standing over here and this wave is impacting you and it's coming towards you and it's impacting you, you're going to get fewer waves per second than you are with this wave down here. You're going to get more waves per second hitting you, and that's a higher frequency. That also means that you're going to get higher energy, more energy getting to you. So thinking about the previous slide and that violet light, blue light has a higher energy, higher frequency than red light. All right, red light has lower energy. Violet light has higher energy. That would be an example of this. So wavelength is a measurement from one wave to the next using the same part. Easiest to measure at the crest. Questions about wavelength? All right, if you have any questions, go ahead, put it in the chat. The next part is amplitude. So we know amplitude because we experience the amplitude of sound waves as volume. That's how loud a sound wave is. All right, and so this is the easiest to think about with sound waves, right? The amplitude is the height of the wave as measured from the middle. Right? It's how far the wave displaces from the middle. So this displacement here. is your amplitude. And we see wavelength also on this diagram, just to remind us what wavelength is, but that's amplitude. The greater the amplitude of a sound wave, the louder it is. The lower the amplitude, the softer it is. So that's a real life connection that you can use for amplitude. An amplifier is a piece of sound equipment used in order to make those sound waves bigger, in order to increase that amplitude and make it louder. All right, now we see a whole lot on this. We see amplitude, we see wavelength, we see a few other things. All right, so to go back for a second, amplitude, the greater the amplitude, the greater the volume of a sound wave. Okay, the more this stretches, the higher that sound wave reaches, the louder it will be. So here we see all this vocabulary and more in the same place. And I've got all sorts of stuff in the way here. The wavelength we see as from crest to crest. We could also measure from trough to trough. There is this part of the wave called the node. The node is where it meets the x-axis. We see the amplitude is between the x-axis and either the crest or the trough. And then there are antinodes. Antinodes are both the crest and the trough of a wave. So the single wave, the antinodes would be the topmost and the bottommost points. The wave speed is how long it takes one wave to pass by a single point. So if you envision, let's say we draw a line right here. Let's draw a line. Let's not just say we draw a line. Let's actually do that. So if we draw a line right here, and this wave is going in that direction from left to right, the wave speed is the amount of time it will take for this one wavelength, to pass by one point. And so we need the wavelength as the distance, and we need the time as seconds, as we need the time that it takes. And that will give us wave speed. All right. Oops. And then finally, we have this concept of frequency. All right, frequency increases as wavelength decreases. So this is a 1 with 4 zeros. That would be 10,000. This would be a 1 with 8 zeros. So that would be 100 million. And going up by 4s, we'd get, this is what, a quadrillion? Or a trillion? I forget. Basically, it gets super high frequency very quickly. So looking at this wavelength is decreasing, 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 and that means the frequency increases. The frequency is the number of waves that pass by a point per second. The frequency is the number of waves that pass by a point per second. So gamma rays is what we call electromagnetic radiation in this frequency right here, are able to penetrate or vibrate atomic nuclei, the protons and the neutrons that are in our atoms. Right? Gamma rays are so small and so high frequency that they're able to vibrate those atomic nuclei. Gamma rays can be really dangerous. Now, X-rays, as we know, can be dangerous as well. Too many X-rays is a bad thing. All right? And X-rays can detect individual atoms. That's how small we're talking about as far as a wavelength. All right? They are very high frequency. Ultraviolet radiation, we know, can influence molecules like the DNA of our skin cells. All right? That's a lower frequency than X-rays, but still a higher frequency than visible light. All right? Visible light has about the frequency of protozoans, simple organisms, meaning the size of that visible light is about the size of a protozoan. Infrared light, that wavelength size, is about the size of a needle point. All right, a much lower frequency than anything else we're talking about here. Microwaves are actually super long compared with everything else here. And it's a little misleading because they're called micro, right? But microwaves are really long. In fact, their wavelength is somewhere on the order of a centimeter. And then radio waves can be tens, hundreds, or even thousands of meters long as far as their wavelength, which means that they have a really, really low frequency. But the frequency is what you're tuning to when you tune in a radio. So when you tune into 107.9, that's 107.9 what is called megahertz, million hertz. All right, so somewhere around here would be 107.9. So radio waves have a really, really, really low frequency compared with everything else, meaning they impinge fewer waves per second than something like a gamma ray that produces a ton of wavelengths every second on the order of 10 to the 20th or greater. Questions about frequency? All right, I'm not seeing any questions. I'm going to assume at this point that you guys have an understanding of the different parts of a wave. And then this last piece is really interesting. So it actually tells us, it's kind of like saying, here's approximately the amount of energy that each wave produces. So things that produce radio waves are really cool. They they produce almost no energy, almost no like heat energy. But then the things that produce ultraviolet or X-rays or gamma rays can get super, super, super hot because that has so much energy in it. And that's why we see, you know, infrared, that's producing heat that we can actually feel. Somewhere around infrared and visible light is where we get temperatures that are comfortable for humans, which should make sense because that's what our sun is producing. And we are far enough away in order to get not burned to a crisp, but also receive most of the radiation energy from this infrared and visible light. Okay. I still don't see any questions on the chat unless I'm missing something. So let's go to Waves on a String, Remote Lab. Open both the Google Docs and the PHET lab, Wave on a String. So when you open this simulation, you will see it's going to start with this, and you're going to see some options. I'll walk you through these options real quick and then let you loose doing the lab. So you can choose to manually make waves. So you can grab the wrench and make waves. You can choose to automatically oscillate, which means that it creates a wave for you. Or you can choose to do the pulse, which means that when you hit this green button, it starts a wave, but only when you hit the green button. So for the other end, right now you see a C-clamp. That's what that's called. And you could have, so the C-clamp is fixed end, meaning that this end is just fixed to a point. Loose end, meaning that when you make the wave, it will allow the other end to travel up and down. And then no end, meaning it continues on infinitely. All right, so you won't see any wave reflect back in the opposite direction like you will with the loose end. You'll see that wave reflects back. And with fixed end, you definitely see it reflect back. You can choose slow motion or normal. With slow motion, it allows you to see every single step of the motion in more detail. There are some options down here. We can choose damping. You'll see what damping does really quickly. You see that it dampens or it reduces that amplitude, the energy in that wave. So if we put it in the middle, we get normal damping. We can also change tension. If you make tension low, you notice how it takes a long time for that wave to do what's called propagate, to move down the whole string of beads. If you increase the tension, then it moves down quickly. It increases that wave speed. For a few of these, you're going to want to have the rulers on so you can measure the wavelength. You can also have the timer in order to try to time how long it takes a wave to move through. Notice that you might want to change the tension and slow motion in order to be able to time it well. So if we have slow motion on, you notice that the timer is in slow motion as well. So it allows you to get a realistic idea of the frequency. And then there's what's called a reference line, and this can enable you to see a point on the wave. so that we can see if it reaches that point. Then we can manipulate that reference line depending on what we're trying to measure. What it allows us to manipulate and then be able to tell when this wave crosses that reference line. That's how you use this remote lab. And so I explored it for you, but I want you to explore it as well. And I want you to start by explaining your understanding of waves, some characteristics of waves. And then you're going to follow these instructions, put your answers in these boxes. Okay. And then you'll see you're going to apply your understanding. That's that last part. Most likely we'll get to that on Wednesday. I have a feeling you'll spend most of your time playing around with these different options and defining what we just defined in the lecture in your own language. Questions? Is everyone still here, or do you just have Zoom on in the background and you're in fact reading a really great book and hanging out in your hot tub? Okay. It's hard to teach when you don't get any feedback, I'm telling you. Okay, so you should be working on waves on a string. And hit me up in the chat if you have any problems, concerns.